Hello everyone. Welcome to this video that's going to walk us through how to make histograms in Kaleidagraph and to fit Gaussians to those histograms. As we'll talk about later, we might want to fit double Gaussians or some other functions to histograms. We want to fit functions to other curves, and we can walk through that as well, maybe in a different video. We'll see what we feel like. At the end of this video, we could add it to this one as well, but maybe we'll stick to histograms here. So what I'm going to do is I'm going to show you data here in Kaleidagraph for a star. So I've taken this data and I've cut it out of spreadsheets that look like this. The way I've done it is I just highlight a row like that, and I'll copy it, and I'll go over here, and I'll paste it in. And then if I highlight everything across there and say, let's transpose it up here. Under transpose, it turns it vertically like that. But I'm just going to get rid of that. I just wanted to show you how I made that, that column of data. This represents 3 years, not 3 consecutive years, for reasons that we don't need to go into right now. It has to do with data purity of the stuff, that the data that I've got around. But this is 3 years of the mean signal, the mean brightness, if you will, of a given star, what we call star 16, on for each night that was clear enough for us to take data. We take data from the 1st of March to the early October, and every clear night. And so this is every clear night for 3 different years down through there. Now, some of the data you'll see is masked out. And you can mask data out by going in and doing this, a function mask, or now function unmask. Okay, so it doesn't get included. If it's masked out, it's as if that data point's not there. So if you have data and you don't want to get rid of it, which is probably a good idea, keep it hanging around in case you want to use it for something else, or you decide you need it, or whatever later on. Keep it there, mask it out. We mask certain nights out because they didn't pass quality tests. So we test the data on a given night. And hopefully this sounds like your Physics 182 lab, right? This is what we do. We test each and every night we take data and say, did the data look like it was good enough? Our what we call photometry. So we do photometry tests. Photometry is the measurement of the brightness of stars. And so we do photometry quality tests. And if they don't pass the photometry quality test, we mask those nights out. And we actually do that very, very, very much like what we're talking about doing here today. We make a histogram and we fit a Gaussian into that histogram, and we look at outliers from that histogram. We don't fit Gaussians anymore. We did in the early days, but we've done it so much we know what they look like, and we know how to exclude nights. Maybe I can show you that in class at some point, or walk through another video if you want to see another video about this. But anyway, that's where this data comes from. So you see that there's several nights masked out in there. I think there probably should be some more, so there may be some outlying nights that didn't get masked out that should have. But there's 107 data points, not counting the ones that are masked out. So the ones that are masked out would be excluded from that 107 data points in there. So what we're going to do is we're going to take star 16 here. We're going to make a histogram of these 107 individual nightly mean signal values, and we're going to see what that looks like, and then we're going to fit a Gaussian to it. So the way I do that is I come up here, and in case I haven't shown you this, I'll just walk you through some other things as we go along, right? You all, I think by now, know how to do the down chevron to get column numbers if you want to do that. If I do a Control F, I get the formula entry window. You see that I have a bunch of formulas stored in here. You see there's a nice one. It says that I want cell 03, which is a particular cell up here, to be equal to the mean of columns 0 to 27, cell 2, row 2 across there. So we can walk through how to do some of that more complex stuff if you want to do complex things. There's how you find the standard deviation of rows 1 to 30, row 0, columns 1 to 30, excuse me. And you can play with these sorts of things, but you see I keep a whole bunch of stuff stored in here all the time. And as I've told some of you, I have a Word document going with dozens, if not hundreds by now, of these sort of formulas that I can just cut and paste into Kaleidagraph anytime I want to. So there's that. If I want to do that, here's another helpful tip. So we'll just do a few helpful tips. If we don't like the format of that data, the way that data looks in here, I do a Control K, and a Control K allows me to change the format of the data in the column right there. So for example, let's, so I'm going to keep that because we're going to use that. So I'm going to go back over here and I'm just going to go Control C, and then come out here to column C and do Control V and paste it in. So now I'm going to play with this column and not mess up our data column. I could say, let's make it a double precision data. So now it's double precision. So it's got more decimal points of precision in it. I could say, this is really integer data, which it is, and I could apply it, and it writes it as an integer. I could say, let's go back to the float format that we had before. Okay, and apply it. But let's say we want fixed. And then it writes this, and it gives me 5 decimal places out there. Or maybe I want 1 decimal place. Okay, apply it. Or maybe this isn't this format at all. This is actually text. So I can apply text. So now suddenly it's text. And if you can't do a formula entry, if you get frustrated and you're looking at it and you say, the formula entry is not working, the formula entry is not working on my data. And if you cut and pasted it in from Excel in particular, it probably pasted it in as text. It can't do formula, it can't do math to text. That just makes sense, right? And so check to make sure, do your Control K and check to make sure that your column is not text column out in there. But you can turn it into dates and times and integers, whatever you see out there. You can do all kinds of stuff with this. Let's just delete that. Clear the data from that column. And by now you probably know how to make a header up here this way. Double click on that. So you got *16 up here. You can drag columns wider if you need more space out in there. You can do all kinds of stuff like that. So anyway, enough of that sort of data messing around, and we can do more. Ask me in class, ask me in lab, and I'll show you how to do stuff. But I'll probably shoot 2 or 3 more videos just because it's kind of fun to run through this and for me to think about this in a more formal way. I've done this for so many years. I know how to do most of this stuff inside and out and without thinking about it. So what I do when I want to make a histogram that I want to fit a Gaussian to, the best way to do that is to come up here under data, under functions, and say bin the data right there. Okay, so let's bin it. And there it is. It tells you the range. It's going from 200,000 to 500,000 in our signal measurements here, and it's made 6 bins. It's going to plot the data at the left edge of the bin, and it's going to make a step plot. Step plot is what you want here, always. You might play around with this and see how that changes your fits and changes your data. Sometimes I like left edge, sometimes I like center of bin. Anyway, you'll see what this looks like. You see there's no data above in these 3 big bins up here. So what we can do is we could go down and let's make this 3.2. So 200 to 320,000. Recalculate. Okay, there's still a lot of space. I didn't do that right, did I? 2.3, recalculate. Okay, so now I cut it too much. It tells me 88 samples fell outside of my range. Okay, so that's too much. So I want to cut it down, not quite so much. So let's make it 3.4 and see what happens. 2 samples fell outside my range. Okay, let's make it 3.5. No samples fell outside my range. Very nice, very nice. Okay, so all our data's in there. You see that most of it is in this 1 bin up here. So what I'm going to say is 6 bins is too few. We got to spread those 88 out. So let's try making 12 bins and see what happens. I did spread it out some. You see it's spread out there. And we can look down through there and see that still most of it's in the top 2 bins. Okay, I'm going to go immediately, instead of 12, I'm going to jump right up to say 48, 4 times as many bins. Okay, now we're starting to get something that looks like a histogram. To fit a Gaussian, as I told you in the other video that we shot the other day, you need significant data do a really good job, you need significant data in 6 or 7 bins right here. 4 absolutely minimum. So this would be an absolute minimum for what we would want to do, but we can do better than this. Now we need enough data that the noise isn't going to eat us up, the scatter from bin to bin. But let's try one more 96 bins instead. Okay, I like that. I like the way that looks. It's a significant number of bins that have data in it. And if we keep cutting, each bin up here is going to have too little data in it for us to be able to do much with. We might try, let's try 120. Still looks pretty good. We got 1, 2, 3, 4, 5, 6, 7, 8 bins maybe that have data in the real data in them. Most of that's in 3 bins, so it's not perfect, but you're never going to have a perfect distribution like this. If we go too much more, let's take that to 120 and make it 400. 400 is the most Kaleidagraph will let you do. There may be a way around that. I've never tried to look for it. I've never needed more than 400 bins, but I could imagine a scenario where you did. So let's make that 400 and recalculate. And you see it starts to get a ratty look to it. It's not terrible, actually. But it starts to get this look to it where it's sort of ragged from the noise that's in there. And you see that it's mostly noise in there. So now we have data in a lot more bins, but no bin has more than 9 in it. And a lot of them have 5 or 6 or 7. And the noise, we'll talk about this as the semester wears on. And I talked about it in the other video a little bit. That's Poisson noise, Poisson counting statistics. And we want to mess around with Poisson counting statistics. It goes as like the square root of the number. So if you have 9 counts in there, your uncertainty is something like the square root of 9 is 3. And 3 is a pretty big significant fraction of 9. 2 is a very significant fraction of 4. So these are pretty noisy things, and you get a lot of jumping up and down, like that 2 that's tucked in between those 2 9s, and that 3 between that 9 and that 6. That tells you, that gives you a sense of just how noisy this is. I'm guessing we could do a good job of fitting that, but let's not. Let's go back to what we had before, or something like what we had before. Let's try 150 and recalculate that and see what we look like. So at 150, we're starting to get a little bit of noise scatter in here, but we've got this thing spread out. I'm gonna chop it down a little bit more. I'm gonna go back to the 120 we had. I think I liked that better. Again, I don't think it makes a big difference, but there you go with the 120. And what we got at the left edge and a step plot. We're gonna copy it to the clipboard. Push that button. I push it twice just to make sure. Third time. What the heck? Okay. Then I'm gonna open a new window. We could write it in this window we have, but I don't like to mess up that data. And so I'm just going to do a Control V and paste it out. And there's our data. This is the data that's been written in the, that's our value, our signal value here. And this is the number of things that are in the number of measurements in that bin range. Okay. And each point is plotted twice. So it's going to give us a nice square top histogram like we're accustomed to seeing. So let's go up here and let's do a linear line plot. 99 times out of 100, if you're not making a histogram, you want to make a scatter plot. Don't connect those dots, because connecting those dots implies to people that you know what's going on between the dots, and you don't. You didn't take data between the dots. You only took data where the dots are. But since it's a histogram and we've plotted each point twice, back over here, we've plotted each point twice. We want to connect those. That's what histograms look like. That's what histograms do. So let's do a line plot here. Normally you do scatter. So we're going to do that, and let's see what it looks like. That's a beautiful thing, right? Okay, so I'm going to show you how I mess around with a Kaleidagraph plot here. So I'm going to move that in a little bit, and I'm going to say that's the number of nights that had that measurement, okay? And that's our signal in ADU. That's a mean signal in ADU. Look at me making a beautiful histogram here. And then I'm going to make that start at 0. I don't like that -5 there. Okay. And I'm going to get rid of that. That label is telling me that's star 16 we're looking at. But instead, I'm going to label the graph up here and say this is a 3-year histogram, star 16 mean signals. Let's capitalize that too. Okay, that all looks pretty good. Now, I'm going to make this range not quite so big too. This looks like it can go from, look, I think we can get all the way down to probably 350,000 on this end. Let's try it, 3.5. And on this end, it certainly can go to 2. Probably can go a little bit above 2, 2.1. Now, if you wanted to blow this up, so that's perfect. That's what we want to do. If we want to blow up on this region, we will in a minute. You can expand this. Be careful if you're about to do a fit to the data here. Look at that. That looks like what you expect a histogram to look like. And be careful if you're about to do a fit to the data like this, because if you're about to do a fit here, and you've cut this so that you only see this region, you might think you're only fitting this region, but you're not. It's using your data file over here to do the fitting. And so you're actually fitting the whole thing, even if you can't see it on your graph. And so you want to be a little bit careful about that analysis. And to say, if you don't want to include these points in your fit, you need to go mask them out and replot the data. Don't just assume that it's not using them in the fit because you don't see them. Okay, let's go fit a histogram, a Gaussian to this histogram. This is beautiful work. It's under general, and there's Gaussian down here. We select the column we want to use. Yours looks slightly different than this. I have an older version of Kaleidagraph installed on the machine I'm using here right now. And we need to define it. So we click what we want to fit. We say okay in a second, but we need to define this. There's our equation for the Gaussian. What we've included is an M1. That's a variable that's going to be fit. Everything that's M is a variable, so there are 4 variables that are going to be fit: M1, M2, M3, and M4. And the variables that are going to be fit, a lot of times if you're fitting a Gaussian, what you might want to do is you might want to not use M1. That's a float. That's a background. That's just added on to your Gaussian. And that's the background on which this is floating. And you might or might not want to use that. That might skew your data. In this case, I like to use it because it's got these points are different. There's something different going on. We're going to talk about in a minute with these points than with these points. That's not just random noise there. And so I really want to exclude those points most likely. And so I want to float up on top of those points. And so there's the M1. Out here's a starting value for M1. Go watch the other video and I explained to you why we need to start close to the expected values. So it can, as it changes those, it sees a little curvature in the space. It sees a little better fit and it knows where to move. So I'm going to give it a starting value of, let's say, 0.2 as a background. Okay, not very sensitive to that data at all. M2 is what's multiplying your exponential that makes your Gaussian. Okay, your exponential that makes the Gaussian, when M3 is the mean and M4 is the standard deviation. When x is equal to the mean, then you have e to the 0, and this whole thing becomes 1. So whatever multiplies your Gaussian out front, the maximum value, it's going to have its maximum value when the exponential is at the mean. So I come over here and I look at this, and it's hidden a little bit by this box, but you can see that the mean, the peak of the Gaussian, the mean is up here around 20 someplace, between 15 and 20. So I'm going to say 18. It's really not sensitive to M1 and M2. M1 and M2 are these big things that are outside your exponential. And if you miss by a fair amount with those, it's just fine. It's not going to actually change what's going on there much at all. It's still not going to blow up. Inside the exponential, that's your mean, that's your standard deviation. These things are squared, and inside an exponential, it's very sensitive to those things. So we probably should have blown this up to look at it better or gone over to the data, but with these boxes open, I can't do it. So let's just try it. It looks like the mean is going to be somewhere in the neighborhood of that 340,000. Okay, so I'm going to try 340,000 as a starting point. That may not be close enough. We may have to make that better. And then the standard deviation looks to me like it's going to be the width across here. Oh, goodness. 320, that's maybe 330 right there. 335, 5,000. Let's make the width be about 1,200. That may not be good enough, and it'll tell us right away if it's not, okay? And we could have done statistics with this column to find out. So let's say, okay, And let's say, okay, and see if it fits. It fit it just fine. Beautiful. Okay. I'll show you in a moment what happens if it doesn't fit it fine. So I'm going to go up. I don't like that black curve fit on top of the black data line. So I'm going to go up and I'm going to say, actually, I need to get, I need to change my legend. I got to restore the legend. Remember, we took the legend away. There's the legend. Now, if I click on the legend, I want to say, there I go. I want to fit it. I want to click the line inside the legend. Variables in black. If what I do is I've made the dots on here this little tiny dot. If your default is one of these bigger dots, you usually don't like to see that on a histogram. You just want to see those smooth lines on a histogram. Okay. Curve fit setting. I'm going to make this red so it pops. Okay. And if I want to make it thinner or bolder, I'm going to make the curve fit 5 so it really shows up on there. There's that big fat curve fit on there, right? That's a little too much. So let's go make that a little bit thinner. Let's make it 1.5. Okay, that's too thin. So we're going to go back here and we're going to say curve fit setting is 3. Pretty good curve fit on there then that we can see. So I like it. I like the looks of this thing. The mean, the best fit mean that it had was 3.3534 times 10 to the 5th. And the standard deviation, never mind that it's negative, because it's really, what it's really fitting there is sigma squared. And so it could be negative or positive. The standard deviation is 3,131. We gave it 1,000 or something to try. And so that's great. We record our values. It said that we gave that an 18, and we gave that a 0.2. So we were pretty close when we started, and it found good values out of there. But we would say the mean of these nights is this 335,340 plus or minus 3,130. Okay, so that's our fit plus or minus 3,130 divided by the square root of n, which is about 10. So about 300, plus or minus 300 or so is our uncertainty. Let's blow it up and look at it a little closer. So we want to blow this up. Let's make that axis go start at about 3.2. There's our Gaussian. Never mind that choppiness that it did with the fit right there. But that's a pretty good fit in Gaussian, right? And so we did a pretty good job there of finding our data and fitting it and getting the values that we want out of this thing. So this is what you want to do with your data, with your n values. And this is and what it did, as we talked about in the other video. If you haven't watched that other video, it's really worth going watching the other video called Histograms and Gaussians, and to look at this and to say it really minimizes the impact of these outlying nights that are out in here. We had all these outlying nights that were scattered out through here, and there's not much impact from those nights. If you just did a column, so let's do that. Note what we got here: 335,340 and 3,130 for our mean and standard deviation. Let's go over here and do column statistics. Statistics of that column, it says the mean is 326,000 versus the 335,000. So 9,000 difference in the mean, and the standard deviation is 26,000 versus 3,000. An enormous difference. Why? As we talked about in the other video, that's a tail wagging the dog effect. You got those few points that are way out there on the tail of this distribution, and they're making a huge effect on the mean and standard deviation. Now, maybe you need them to. So my recommendation to you is always do this work fitting a Gaussian. Sometimes your data doesn't clean. You can't get a good Gaussian fit. And also do it with the column statistics both ways. And kind of compare and think about what's working best for you. Now, I'm going to tell you, I'm going to do 2 more things. We're basically done. This has turned into a long video, and I don't want to take too much more of your time. But this is a lot of really good mechanical information in here you're going to use to do your homework, and you're going to use to do your work for class with the lab when you're doing your lab write-up. And you see the power of doing the Gaussian fits here. But I want to show you what happens when a Gaussian fit goes awry, or any kind of fit. And then I'm going to show you what happens when I want to show you, before we do that, let's go over here to PowerPoint. And let's look at this. What we're looking at is star 16 right here. Star 16 is an eclipsing binary. An eclipsing binary is two stars that we actually see as a single star. They're so far away from us, we can't resolve the two individual stars, and we see one single bright point in the sky. But the orbital plane of these two stars, they're orbiting around each other, and the orbital plane is such that one star periodically passes in front of the other star. Then the other star passes in front of the first star, and it goes back and forth. So when you look at a curve like this is a nice, beautiful curve. Star 1267, this is. Both stars, both stars, both stars. Wait, it's going into eclipse. Going into eclipse, going into eclipse. One star's blocking the light from the other star. Now it's crossing the other star, and it's got the maximum amount of light blocked. And now it's coming out of eclipse, and we see both stars again. Likewise here. Both stars, eclipse, out of eclipse. Into eclipse, into eclipse, into eclipse, maximum eclipse, out of eclipse, out of eclipse, out of eclipse. And this is the star that we just made that graph of. These are the nights. If we make a graph like this, if we don't want to make this plot on every night because we don't have time and we're tired, we want to watch TV or something, we don't want to make this graph for every single night. We just want to pick the nights that have the eclipses because we want to fit these eclipses. We want to find the time of minimum. That tells us a lot about what's going on with this star. We don't have time to talk about that right now, but that's part of the research work that I do with students is we time these eclipse minima to see how the two stars in the system are interacting with each other. And if we don't have time to make that graph every night, we know which nights we want to make the graph. The nights where the mean was less than we would expect. So these nights out here, the means are very much less than we would expect. Those must be the nights that it's in eclipse. And in fact, it is. If we go make this graph like this, what you're seeing here in this graph is every dot is 2 minutes. Okay, we were making every night was every point in here was a mean over the course of a night, and this is within a night. This is a dot every 2 minutes within a night. And so what we see is that when it's in eclipse, it gets down close to, not quite, but it gets down close to half as bright as, so it says about, each star in the system is about, or they're pretty similar, because if it were only down here at the bottom, we might be half as much light as we were at the top. And you see this is getting down close to half as much as this light up in here. But it's not all the way down to half because we're averaging, and we're averaging over the time that it's going into eclipse and the time that it's coming out of eclipse as well. So we're learning a lot from this histogram. It's really helping us go find the nights we want to find to fit the points. To get the data that we want to get, and then maybe time those minima and check to see if the depth is varying and so on. There's all kinds of things we want to do right there. So anyway, that's what we got going on. That's good, powerful stuff. I want to show you one more thing that happens if we did a poor job of fitting this data. Let's go back up here on the curve fit. We'll go back to Gaussian. You have all kinds of choices here. Wonderful, good stuff you could do. And under general, you got wonderful, good stuff you could do too. Let's go back to Gaussian and deselect it. Okay, it's gone. Now we don't have our curve fit. We can try a different curve fit. So let's go up here and let's go back to Gaussian. And let's define it again. And instead of giving it 340,000, let's suppose we typoed it and made it 34,000 for the mean. And we made it 12,000 for the standard deviation. I don't think that's going to work. That's too far away from the starting point. Yep. It blew up. It says, wait a minute, singular coefficient matrix. We couldn't find any curvature. It never found a curvature, and it gives you this flat line along here, and it gives you values that it gives you your starting values back. Those are the values we put in to start with, and it says error. Don't trust that error anyway. We can talk about what that means, but it's not a real error in those parameters. And so as the semester goes on, we can talk about that more. So that didn't work at all for us. So you see, you have to start close enough to get the fit. You can tell just by looking at that. That didn't fit that Gaussian. So okay, very good. That's what we got for you. Pay attention to this, see if that helps you do your homework for Thursday, and see if that helps you get your lab analysis done after this first lab. And we can shoot a few more Kaleidagraph tip videos as the semester goes along. I know Kaleidagraph better than I know MATLAB. you could, MATLAB, okay, but I've been doing Kaleidagraph for decades, and so I've got it. I can sort of do this in my sleep. So anyway, let me know if you have any questions after you take a look at this. Do take a look at this all the way through. Here at the end, presumably you already have taken a look at it all the way through, and we will see you later.